Okay, just an audio check. Is my voice coming through? And I think I have my camera enabled via the web browser. Hopefully you guys can see me this morning virtually, but honored to be here. Thanks for the invitation. And I'll just have to say that, it's a privilege to be a part of this team. I'm really looking forward to the effort. It took some time to get the effort in place, thanks to Lockheed Martin management, all the way up to Eric Schrock and Dr. Robbie Mandelbaum out at the Advanced Technology Lab for really enabling Lockheed Martin Aero to team with Lockheed Martin Advanced Technology Labs to work with the University of Illinois for the NASA RMD project. So I am super excited, and we've officially begun the effort. So I'm considering this essentially a kickoff, and I'm looking forward to working with all of you and learning more about how we can help transition some of the technology. So one of the things that I've been working on at Lockheed is L1 adaptive control. We hosted a great panel session with Dr. Hovakimian at the AIAA SciTech, with Dr. Irene Gregory as well, Dr. Brian Holm Hansen, and Dr. Maruthi Akella. And we're all excited about L1 and what steps we're trying to take to mature it and move it into other platforms. So a little bit about myself. Um, Native Texan. I've been here all my life, raising a family here in Texas. I grew up in Houston, Sugar Land, started my career at Johnson Space Center after UT Austin, Hook 'em Horns. Went to NASA and trained astronauts in robotics there in the MRMDF for moving space station cargo modules from the cargo bay of the shuttle onto the space station for the International Space Station. A great start to my career. Moved to Fort Worth to aeronautics in the 2003 timeframe, working the Block 60 F-16. And then once I started that program, I started my graduate career at the University of Texas at Arlington under Dr. Dogan, Attila Dogan, and worked on aerial refueling for my master's of science, and then went on to a PhD with him in distributed control allocation, which was inspired by quantum computing, among a number of assets that I've worked in the skunk works. So it's been a great 25 years, and I'm looking forward to the next 25 years of aerospace engineering. I've managed to recruit someone that I'm really excited to work with, Dr. Carly Malika. I don't know if she's on the phone today, but we're working to get all the logistics in place to get a cadence going for this ULI effort. We'll both be supporting this at a part-time level, but really we're really looking forward to meeting all the SMEs across the team and looking to transition these types of learning elements into maturation paths. So Dr. Malika is in New Jersey. She's at the Advanced Technology Labs, and again, I see her as really a champion that's just privy of a bunch of different projects across the corporation, and is going to be a great voice, a great advocate for us for what we're doing here to move into the advanced urban mobility. So some history on adaptive control predates my career. This dates well back to the 90s with my recently retired colleague, Greg Talent and company, where they did some restore work in the 90s. I think we heard about some of the restore efforts historically from some of our audience members there at the SciTech, if you were at that panel session. So that was a great effort, I believe, hosted by AFRL up at Wright-Patterson Air Force Base. And then it moved into kind of the V&V flavor of intelligent and adaptive control systems in the 2006 timeframe. By that time, we started to have momentum with the S5 conference, which was the Safe and Secure Software Systems Symposium. That was an annual symposium that was hosted by AFRL up in Dayton every year. And that's actually how I met Dr. Hovakimian there, as we were talking about what measures can we take for V&V of these systems that could potentially be non-deterministic. We knew it was going to be a very difficult problem, and there was a tremendous set of folks working on some of those different techniques for these systems. I'll mention, some of the major topics were runtime assurance. Other topics were formal methods and reachability analyses. And I know several of you on the phone are aware of some of that effort. In the 2017 timeframe, we started the Smart Adaptive Flight Control Environment, IRAD, which is our Lockheed Martin internal funding, just research and funding, and that's where our team has grown since that time. We've had several papers in the AAA and IEEE, and really the group has migrated towards the L1 adaptive control is one of our favorites, and I'll talk a little bit about today about why it's one of our favorite architectures going forward. So here's a few of the publications that we've released. If you would like those papers, you don't have access to those, just reach out to me. I'd be glad to share them with you. Now that we lost 10 minutes on the hour, I'll probably go through these slides really quickly, but I always use these slides as kind of a way to motivate moving forward with intelligent systems and autonomy and what we're trying to do with adaptive control systems. But this is one of the fun slides where I kind of go back to the meaning of autonomous, where it dates back to one who gives oneself their own law. So some nice pictures there, and some links back to the old 2001 movie that we've all seen and grown to love, with the HAL autonomy that grows a spirit of its own, but not open the door for Dave. But one thing I like to do is talk about MIT Dr. Howe's degrees of autonomy that he's briefed over the years, where he came up with a means to categorize these systems in terms of what is the human out of the loop aspect of that, all the way from basic autonomy with remotely piloted assets to systems that begin to diagnose. They have integrity monitoring, they adapt to uncertainties, they reconfigure, from single agents to now multi-agents and group coordination, group goals, and then fully autonomous systems with no humans in the loop. So I distinguish this as different tiers of autonomy, between the basic nav to systems that self-govern and multi-agent autonomy, and to advanced autonomy. Obviously, that's where we're trying to get, right? For the Star Wars fans out there, R2-D2, BB-8, that's where we're trying to get with these systems that can adapt to the systems that are the stimuli that are not known a priori. And there's easily a hook in here for L1, and I think some of the learning elements that we have in our RRA proposal. Another professor that I've worked with in the past that I'm a big fan of, you may have met him, Dr. Frank Lewis at the University of Texas at Arlington, who's taught years of coursework in distributed control, optimal control, intelligent control. And I've gone through several of his courses. He was on my graduate committee, and he's just a half-hour drive from here at the UTARI, University of Texas at Arlington Research Institute, and just a great asset in terms of systems that are intelligent and adaptive. So that could be someone that I reach out to actually as a part of this ULI. I think he would be a good advocate for us in what we're trying to do. But I like this reference with Sardis. He kind of breaks out, autonomy and systems that adapt and learn across these different categories, from organizational level, think of outer loops and lower frequency updates for path planning, all the way down to the execution level. And I'm really looking at the L1 adaptive control piece as that high rate, that fast inner loop piece that's going to ensure robustness, ensure the pointy end stays forward, right? Ensure we have good stability margin. And then these different learning elements going all the way out to that organizational level. So I liked this chart. It really resonated with me when he walked through it. I have a danger of going off into the philosophical means of autonomy and adaptive control systems. I won't play this link here, but I always come back to, at least my students, relating autonomy and adaptive control back to this means of intelligent systems and maybe this extra branch on the tree of life for the 10th degree of autonomy. The link back to this video is really nice. Basically in 40 seconds, Carl Sagan goes back 4.5 billion years from the single cell organisms all the way to modern day life. So really cool video. I'll share this link with you. Go out and take a look at that. All right, so in terms of aerospace platforms, it's inspiring to take a look at all the great work that's being done across the aerospace industry and NASA, government, academia, and there's a bunch of different types of problems. And we can see that just the complexity of the effectors alone, I think, is driving the need for these types of systems that will improve online and really reduce the need to go through the expensive V&V process. And the V&V process, verification and validation, we're all very aware of that, but I'll show you a couple slides here going forward in terms of the flight controls synthesis procedure that we go through in that V&V process, and that opens up the business case, I think, for the work that we're doing here for NASA. Um, in terms of the flight control synthesis process, this is typically my roadmap for the way I would do business, where I have some kind of complex dynamic system. Obviously, we need the governing first order principles. Think of your Newton's laws to come up with your nonlinear equations of motion. Typically in flight dynamics and flight controls, those are ordinary with one independent variable, time, right? And then to synthesize our control law, we usually have some type of linear approximation, usually a Taylor series approximation, dropping the higher order terms. In terms of a point and slope linearization, there are other methods to linearize, such as a 2-point linearization. There's a good reference there from Dr. David Hollander at UTA for different systems. But usually in flight controls, we use a point and slope Taylor series approx. And then we go into our time domain state space systems. We move into our Laplace transforms and look at the frequency domain of our control design architectures, where we're looking at stability margins, loop crossover frequencies, and robustness, prior to going back via the inverse Laplace transform into our impulse and step responses. So the reason I like to bring up this plot is because I think the L1 adaptive control architecture is conducive to this design process. That's something I'm really a fan of. By going into this classical linear analysis, I can still take a look at what these adaptive systems will generate in terms of that classical analysis. So to me, that is a major strong point and something I'm really excited about going forward. I think it's going to allow us to get our foot in the door on adaptive systems. I know I'm already running out of time because of my my issues with the Zoom, so I'll move forward through this. I don't think you need more business case. Typically between the application, the modeling, the control synthesis, this iterative loop, we know this is very expensive. It can be very time consuming. There's been great strides to kind of merging the models and the control synthesis piece of that design cycle, and I really classify that as a model reference control type of system, where you're trying to bridge those two worlds. Now you have a physics-inspired controller where you're trying to leverage your smarts in terms of that modeling. And I think dynamic inversion and these input-output feedback linearization techniques are really a good example of that, where I have some kind of onboard model that's capturing those nonlinearities. But I'm convinced the future systems are going to move from this inert MRC to something now that's online, right? It's that onboard model piece, or even alleviated an onboard model that's going to adapt and learn online. Why do we need to do that? This is the famous V. We've all seen the famous V, but think about it in terms of concept of operations, where maybe you have one or two engineers defining requirements in terms of what do we need to build. And that goes all the way through these detailed design phases, implementation, all the way out to the top right of the V, where it ends up being very expensive if you find defects and anomalies. So this is just a little heuristic where I was showing, let's assume that an engineer finds a defect at some phase in this V&V process. So if you found the defect in your concept of operations and had to rewrite your requirements document or your basic description document, it's fairly inexpensive in terms of cost and schedule. But as you can see, if you start to find these problems at different phases, what I'm doing here is I'm saying I found some type of anomaly report through each one of these phases. And if I have to iterate and go back to square one of writing requirements, you can see that this is definitely exponential in terms of engineering time. And that's what we're trying to get out in front of. How can I get to the field where my systems are improving online to something that I didn't know a priori? So we're all aware of that business case. Dr. Guo has a great lecture out there online. I don't have the YouTube link for you, but his lecture was move left. We need to shift left in terms of that V&V process. So we've been working for that whole S5 community that I mentioned earlier. How can I move these processes and these tests to the left side of that V to really allow the iteration up front to prevent the expensive fly, fix, fly type of approach? Okay, so all of that as front matter and preliminaries, I finally get to the architecture, the framework that we have for this program. And for me, I'm looking at you as the SMEs across all these boxes and all these TCs. And for Dr. Malika and myself, I I think our role in this is really the technology readiness level and that industrial perspective in terms of, you know, offering insight on how we would transition and field these systems and what we need to do to go prove to our certification authorities what it's going to take to go ensure that it's safe. So really, this is the broad picture from our Step B proposal. And you know, I see the TRL piece and my role in the program as really an element of each one of these TCs as I learn more details on the technology. Notice the TC4 is showing our testing, eval, and integration. So that is one thing that I'd like to leverage, at least with my company, is, you know, what high fidelity simulations can we use to go incorporate elements of RRA to get some realistic feedback on how well some of these approaches are working. I have direct access to, you know, our teams that work with the F-16 Vista. We've built the auto ground collision avoidance system that's been successful for you know, saving pilots on F-16. So, you know, the high fidelity simulations I think are going to be a great path to pursue on some of the RRA framework. All right, so a little bit about SAFE, Smart Adaptive Flight Control Environment. As I mentioned, we've been working on this for a few years, where the first couple of years started off more with a literature survey. As we converged to L1, that became a more involved study into what it would take to go build this type of system. This architecture is showing how we've moved to augmenting a legacy type of system. This is a figure directly from one of our papers, if you're interested. You know, but we've learned that the benefit or the feasibility of L1 or adaptive control in parallel to any legacy controller is a great thing, right? So here we're just showing, you know, a common architecture for a dynamic conversion or a model reference system where you have some type of online control allocation, smart mixer, and I'm showing just a picture there of a plan form that we've studied in the public literature. The onboard model, you know, the classical architectures that we've all grown to love. And the idea is, now can I use L1 in this parallel setting that's monitoring that MRAC error and adapting and improving the achieved dynamics with respect to the desired. And I think we've shown that that concept is a great concept, and it's something that's also what we call bolt-on. We really like the idea of bolting on or bringing on this new element without touching some of these other components that have already gone through some of these TRL maturations. Now I have a system, it's proven, it's a legacy system. I don't want to open that up and change the code in it. I just want to augment that system with some type of parallel piece of software that's monitoring the states of the system and trying to drive it towards a better performance system. So now I really feel like I'm preaching to the choir. Again, honored to be a part of this team. So I don't think I want to go through these details, because I think you should be teaching me this architecture on L1. But obviously the L1 system has the three major components between the predictor. We're using the modified piecewise constant adaptive laws, and we have references to some of those derivations in our papers. And then finally, the control law with the low pass filter is a key element, and something that we also like because it's intuitive. It allows us to tailor it to our actuator bandwidth, you know, commensurate with not shattering those surfaces for some of the high rate adaptive activity. You know, so the equations in terms of the modified piecewise constant laws, which I think are quite elegant if you go through and you do the you know, kind of the continuous time domain approach, and you start looking at the zero order hold derivations of how to remove the error in the system. This was a natural fallout by going to this piecewise constant approach. The modified with the integral control law, this modification term allows us to achieve the adaptive performance at a lower rate. So we're not necessarily having to run our L1 adaptive controls, you know, at 500, 1,000 hertz to achieve the same performance. We've had some recent success by running the MPC laws at the native rate of the baseline interloop flight control system So for instance, in some of the videos that I'm showing you going forward, I think the system was running at roughly 100 hertz or at 100 hertz. The MPC laws ran at that native rate, and we had very good improvement due to this modification term. And then finally, you have the control laws with the low pass filter on the matched uncertainties, the estimate of the matched uncertainties, as well as the unmatched low pass filter on the unmatched uncertainty pieces. And naturally, there's some restrictions on that to ensure that you have strictly proper dynamics. So then recently I've published at the AIAA just on some derivations or extensions of at least the linear analysis. So looking at a linear time invariant system in terms of a input output feedback linearization approach, and then kind of coming up with these analytic equations that first govern the closed loop baseline flight control system with respect to uncertainty. So kind of an excerpt of the paper was showing, the output of the controlled system was a function of the initial conditions. It was a function of the reference or the inceptor commands from the pilot, as well as now I have these channels that come through for disturbance on the output. Right, so these partially open loop disturbances impeding the output of the system from matched uncertainty and unmatched uncertainty, and finally this hook for what we call the incremental or the adaptive commands into the system. And the whole idea, the beauty here of the design is now I have this software implementation of UAD, and the whole goal is I want to go cancel out sigma n and sigma um, right? So what are the dynamics associated to each one of these transfer matrices to go achieve that? And really that's the premise of the paper. And then the paper goes through and it starts to talk about describing that output equation with respect to the closed loop adaptive laws. And I don't want to go over every single equation here, but I really liked some of the work that's been done in the textbook, Chow and Hovakimian's textbook, where it describes what I'll call the washout analogy. And if you think of a washout, basically one minus a low pass filter, it becomes a high pass filter. So to me, the great insight on that was L1 was allowing me to attenuate the matched uncertainties and the unmatched uncertainties within a frequency band, because of that washout. So it makes sense that based on these C1 and C2 knobs, those low pass filters, I can tailor what uncertainties I'm planning to attenuate, as opposed to, the high pass filter where the other uncertainties at high frequency beyond my actuator bandwidth are naturally just going to come through the system. So I really liked this, this piece where that emerged in the closed loop equation. All right, just please interrupt me if I'm going over on time. I see I have 40 minutes after the hour here. The paper also walks through how we formulated the optimization problem, including both the matched and the unmatched pieces there, where we're looking to minimize the influence of the disturbance or minimize the L1 norm of that quantity. So find the correct break frequencies for those low pass filters. We have not really gone beyond the break frequencies of the low pass filters into the different structures of the low pass filters in terms of higher order filters. And I think my colleague on the phone, Dr. Gregory, actually mentioned that can be an open problem, and that could be an NP hard problem, just determining the optimal C1 and C2 structures. But we have been able to solve this optimization problem with different techniques. So really minimize the influence of the uncertainties with these L1 design knobs, such that the low pass filters are DC. And then naturally, to me, this is key. This is something I'm really excited about, and I plan to leverage on our TRL business case, right? Because I can still show with this architecture that I have a gain margin and a phase margin. So we're going through this optimization process, and we're still showing to the certification authorities that I still have those classical metrics, which is to me, a major benefit on the system. There's some publications on this ICE concept, which is this tailless fighter from years ago. It's been in the making over decades of work, but the beauty of this model is it's backed up by both CFD and wind tunnel data from my colleague here at Lockheed Martin, Dr. Mike Nestroy. You can see some of the literature that he has out on this, but it's really a controls challenge with the number of effectors from the inboard, outboard, leading edge flaps, these all moving tips. You have a thrust vectoring system on the pitch and the yaw axes, and these spoiler slot deflectors, and just a flight controller's dream to have that much control power, right? You can move every single one of these effectors to your heart's content, so it ends up being a challenge. So we looked at that system in this AIAA paper that I'm giving you a summary on, and we went through that optimization where we were trying to find, given the L1 architecture, where do I set those low pass filters for matched and unmatched uncertainty to minimize the L1 norm, to gain the maximum attenuation possible on disturbances, but still preserve the margins. So this is just an excerpt again showing, given first order structures, first order filters, I see that I have a limit really on my phase margin of my system. All right, so basically what we're showing here is that as I choose a break frequency, the red line is what we're trying to minimize. That's the L1 norm. And the blue line is showing you, where the margin ended up being for the system. So if I chose a break frequency of 5 radians per second, as fast as possible, up to the actuation limit, of course, I was not limited by gain margin. I still had 14 dB of gain margin in that system. But you can see that as I increased the L1 bandwidth out to 5, really my limiting factor was phase margin. All right, so it stopped at about 47 degrees. I couldn't really go much faster than that because you start to see that graceful degradation where you'd start to have a more lightly damped system. So this was a kind of an interesting insight for us going through that optimization. Going back to the analytic comparisons is always something that I really like because that makes sure that you understand what you're doing. So some of the excerpts in the paper go through the means of finding the analytic closed loop equations in terms of output due to matched disturbance. So the closed loop output transfer function with respect to a matched disturbance analytically, and then compared to the numerical model that we come up with in terms of that ICE linear model and that linear implementation of the modified piecewise constant law. So you can see there's a very good correlation there. And this, so I'm showing you a Bode plot here, pardon the small font, but the x-axis is frequency in radians per second, and the typical Bode plot of magnitude and phase is basically just giving me an idea of a category or an input spectrum and how those outputs change. So if you look at the closed loop system control law with L1 off in this case, you can see that I do have some natural attenuation for disturbance. All right, so this is basically telling me if I inject matched uncertainty into the system, just based on the baseline control law, yes, I get some good attenuation there at low frequencies. There's a resonant peak out in here. So that would be the worst case of matched uncertainties. That would be contaminating the output of my controller, right? But look at the benefit of L1. I mean, this is tremendous, right? So L1 is basically increasing the system type. It's really helping with that low frequency disturbance. And that attribute is something that we've tested just recently and seen some major benefits. So we really love this this piece that L1 is achieving for us. I'll skip over here because I know I just have a few minutes. I want to show you some videos. That's a final time domain of the paper. But so I showed these back in October. If you were on the phone, this is something that actually it was November, I think, when we talked last for one of our NASA TIMs. But this was something we did recently out at the Air Force Academy in Colorado Springs, circa October last year, where we took the L1 adaptive controller, the MPC piece, and we hosted it on this this small airplane. It's made out of foam, very resilient to crashes. Actually, we did end up breaking one wing on one of the glide tests prior to the powered flight and prior to our flight control test. But they fixed it in a matter of an hour. So it's a tremendous capability, a tremendous facility out there at the Air Force Academy. If you're interested at all in that test site, please let me know. I'll put you in touch with the folks that are actively working with the cadets and the students out there. It's just such a treasure of a facility, and we're planning to continue working with those folks. But what I'll say is on the architecture, they had an RGU pilot, which is just a classical proportional integral derivative system for stabilizing this, for controlling this stable planform. but they had a Raspberry Pi 4 companion computer. The companion computer is where we hosted the L1 augmentation, and then the output of the companion computer was summed in to the total effector commands of the system. So I'll play this video again. This is one bungee launch. You see they had a bungee cord set up, about maybe 20 yards out, and once the system detects the air data, there it spins up that prop pushing weed eater noise that you're hearing there in the background. Here's a video, a landing system. So we had some cadets use some basic tracking tasks to try to show differences between our safe off and safe on, which is essentially an L1 augmentation. And they showed immediate benefits in terms of pitch tracking that I'll show you here going forward. All right, I think we have a little bit of time here. I want to give some time for questions because I can't see you on the phone, so I don't want to talk too much. But this is kind of walking through the just classical linear analysis of the control architecture, right? So it's you look at the ARDUPilot and some of the amateur enthusiast control laws for these type of assets. It's basically a proportional integral control system. So we looked at their baseline gains in terms of what we were trying to augment with L1, right? And I'm just kind of showing you what that open loop transfer function looks like. But they essentially have a feed forward gain on pitch rate. You have a proportional gain, an integral gain, so it has an integral control action. Here's the fourth order physics for the plant. That's kind of an inner loop piece, feeding back pitch rate. But they also have a fly-by-wire mode, and that was the mode that we used for our experiment with L1, where now the pilot is controlling pitch attitude. Right, so you basically have two loops. You have a proportional control law on pitch attitude, and then you have a PID construct on pitch rate. So when you look at these different design levers, what you end up doing is you get this is kind of your software, your control law transfer function. You can place a gain in the system, and you can place a zero in the system. You're placing a pole right at the origin, right, just due to the integral control action. So the aspect of this was really interesting, is where do you set that zero and where do you set that gain, right? And that's kind of a classical textbook design where you're considering that. And you're looking at bare airframe routes, right? So for that system, obviously it has a second order, undamped short period mode. It has a T theta 2.0, which is pretty famous. It has an actuator pole out here at high frequencies. But the baseline controller is very slow and overdamped in that fly-by-wire mode. So the pilot would ask for a pitch attitude response. This is linear analysis, but this is pretty close to what we saw in flight test. And seconds later, the system's finally stabilizing and getting to that tracking that you asked for. So you can see it's just very, very low frequency in terms of gain droop. So something that was kind of leading to poor handling qualities, poor response in terms of the controller. And if you go look into that, just in terms of bare airframe dynamics, this is just a simple root locus showing you, I've got this zero TH1, so I've got this dominant closed loop eigenvalue around that regime that's leading to some of that low frequency overdamp behavior. Whereas the ZC term, this is a zero that I was talking about earlier in that control law. And you can see that, the term is not really changing where this dominant eigenvalue is. So that was kind of interesting. And regardless where you set the ZC zero in that feed forward term, you're not really going to change that location of that dominant eigenvalue. So what I'm showing you here between the left and the right panel, the left panel is the base proportional integral derivative control architecture. And then the right panel is now when I'm using L1. I'm using L1 with MPC to augment the nature of that root locus. So there's a couple of things here that are interesting. I'm just kind of starting from the top and going in. You see the short period, it's moving in the right direction, right? So I get improved damping, improved frequency on the short period by moving that away from my imaginary axis. But you take a look at this stuff in here, and we'll zoom in here in a minute. But you have a pole at the origin, right, due to my integral for my control action. I have this 0 from the bare airframe, we'll call it TH1, and then I have this 0 that I'm setting based on the controller, and that's Z sub C, and that's your software implementation. But regardless of where I set the gains in that classical controller, the pole at the open loop pole at the origin for my type 1 controller, for my integral control action, it can't go anywhere. It's stuck, right? So if you go back to your classical root locus analysis, your open loop poles are going to drive towards your open loop zeros. So if I have an open loop 0 at TH1, that low frequency root, regardless of where I set the gain, if I set the gain to infinity, it's going to stop at that low frequency piece. So we think that that's exactly what we saw with that planform, limiting the good response. Now, if you go look at L1, look at the beauty of this. So based on the L1 with the predictor structure, the MPC, and the low pass filter, take a look at what's happening classically near the origin, the pole 0 map. I get this pole 0 cancellation here. I get this, this is the ZC0 that I have, but I have this other optimized loci now from the L1 piece with the addition of this 0. And take a look at this, this locus. This is exactly what we like, right? Now that I'm driving gains up, look at the way the open loop poles are migrating. They're moving in the right direction with respect to damping, and they're moving me away from that low frequency problem near the origin, and also keeping the damping intact. Some more of the same. This is just the same plot, but I'm zooming way in so you can see that low frequency piece. So again, this TH1 0 is just limiting in terms of that classical controller, explaining what we saw with the baseline system. Now you compare to L1 on in the right, and you see the nice cancellation there. You see the dominant eigenvalues end up achieving a much higher frequency with the L1 augmentation on, and that ends up becoming quite noticeable in terms of a frequency response analysis. So this is a baseline system. This is we call that rehost. Rehost is the PID control law. But you see this droop, right? So this is a closed loop transfer function showing you, yeah, I'm just not really achieving my command in here. But with L1 on, all of a sudden I get that augmentation, and I get a much better response out of the low frequency tracking. So summing up, this is the flight test data that we had. I showed you this at the SciTech. Now that I've given you a little more background, I think this plot makes more sense. We didn't really have time in our panel session to talk through some of those details, but this flight test data is showing you essentially what I just kind of walked through now with empirical data, with the base system at the top left in terms of the time history. The pilot's asking for the blue commands. The pilot's asking in that fly-by-wire mode, give me 30 degrees pitch down, give me 30 degrees pitch up, 30 degrees pitch down. And the classical PID controller is never really achieving that in terms of gain, right? It's not tracking that command well. Then I turn L1 on, right? Yes, there's some delay in the system. We're working on improving some of that, but look at the low frequency improvement in terms of tracking, right? So I'm getting much more gain out of the system. When you look at these plots in the frequency domain, this is classical PID controller, blue line, and look at the magnitude improvement due to L1. So as I mentioned earlier, we're getting that increase in the system type. It's really getting much more attenuation on the disturbances and just better tracking in general with the L1 enabled system. So to me, this was a great correlation back to our linear analysis. Okay, here's a little fun video to close out the talk on. Very windy out west. The winds come off those Rocky Mountains at 40 knots, and it was a really challenging environment. We're going out there again at the end of next year, or at the end of this year, with a different planform that's less stable, if not unstable. So we've got some work to do, and that's what we're heads down working now. But we're excited about what L1 offers, and I plan on using this NASA ULI to learn a little bit more about your thoughts on robustness and how to go mature the TRL on these learning elements. But again, honored to be a part of this team. Here's a snapshot of the all hands out there at the Academy flying the Striker asset, and just a tremendous victory there, I think, with our early look at the L1 adaptive control pieces. going to skip over the TRLs. I think we saw this this last time, but I want to open it up and just allow any questions with you. Thank you very much for listening.
Chris, thanks for this great presentation. I had never seen all these details that you showed. By the way, the last slide was showing 2011. Or were those flights done in 2011, or it was
which slide was 2011?
Before this, the video on the top left corner here, 2011, right?
Yes, that's just an unfortunate miscalibration of the avionics. That was not 2011. That was 2022. Yeah. And you know, we just need to report that to the students. The students need to go update the firmware or the clock on those GoPro cameras.
Okay, so let's see if we have one or two quick questions from people. So thank you for sharing your progress, right?
No,
hi, I have a question, Naida. This is Shayan.
Uh-huh.
Sorry, I don't know how to turn on the camera. I'm joining.
Okay, that's fine.
Yeah. So
okay.
again, Chris, thanks for the talk. This is Shayan from University of Illinois. So the first part of your presentation, you were talking about VNV and reachability kind of things. And then the second part, you talked about this interesting application of L1. So do you see what is the next set of challenges in applying VNV to L1?
So the next set of challenges to applying VNV to L1. So that's a really difficult open problem for adaptive control systems. But for me, the reason I've graduated to L1 is because of some of the classical linear analysis that I mentioned. So I think its strong point is it allows me to go use some of those tools to still show the system has stability margin, gain margin, and phase margin. So I feel like there's a door there for us, at least classically, for the the high rate L1 augmentation that we're doing. But in terms of for our RRA framework, we know that we have other elements, learning elements now. So that's going to be a challenge for us. Obviously, we're not going to be able to use stability margins for these things. As a team, we're going to have to figure out, what other frameworks can we use to ensure the safety of these assets, from runtime assurance to reachability. And I think Dr. Hovakimian's mentioned some names for me to consider for help on that aspect. So does that help your question, Cyan?
Yes, thank you.
Thank you.
Cyan, and that's with regards to your question, can we schedule next time you present what you have done with Lean on this V&V so it will tie in well, or in a month, right? So is it possible? Lean can work on the preparation of the presentation, but it's your tool. So I want to get an overview of your tool and how Lean has applied it to L1. Will that be a reasonable presentation for a month?
I think so. I'm on sabbatical this semester, and
I know, that's why I'm saying
yeah.
Link can help you to prepare, but
my
you may
schedule
need
is a little unclear. But a month from now would be what, late March?
right.
Mm-hmm.
Yeah, that should work.
Okay, Link can work on extending his work within the next few weeks more. And I'm sure you have some other overview slides of your tools and how they have been applied in other scenarios. Putting all together, it would be a good seminar for the next time for everyone to listen to. Right?
Sounds good.
Right. Okay. So next time we have Cyan. More questions. Last one or two questions for Chris. Chris, thank you very much.
Thank you.
Beware, if you ask a question, you might get volunteered to speak in a future seminar as well.
Hi, Chris.
Hi.
Thanks for your talk. This is Pan. Yeah, I'm
Pan.
working. Yeah, I'm working with Professor Hovakimian as a postdoc. So in your talk, you mentioned a few times you implemented L1 together with MPC. I'm not sure whether I listen you. To implement an MPC for the flight vehicle?
Yeah, so I didn't mean model predictive control. I meant MPC in terms of the modified piecewise constant. So the typical, the famous L1 architecture using the modified piecewise constant adaptive laws in the textbook and in the literature. So hopefully I didn't cause confusion there by using the MPC
Oh, I see,
acronym.
I see. I see. Okay,
Yeah.
okay. Okay, got it.
Yep. But nice to meet you, Japan.
Yeah, nice to meet
Looking
you.
forward to working with you. Thank
Yeah.
you.
Thanks. I have another question. So at the beginning, you mentioned like a 10 degrees of autonomy, proposed by Professor Hao from MIT. I just want to know, in your opinion, like which level has the current aerospace industry reached?
I would say we're in tier 1 to tier 2 of that list that I showed you. I think we're just scratching the surface. We definitely have not built an R2D2 for the tier 4, degree 10. But my opinion is we're still just at the very, very first phases of that autonomy. But I'm just one person. I only work a couple different things, so maybe someone else can speak to that in terms of state of the art in autonomy.
I see. Yeah, thanks. Thanks for
Chris,
sharing
and one
your
last
opinion.
question. Can we have also a copy of your slides? It will be password protected under our ULI folder so others can access, work around it. Because I want the students to see how you do, for example, robustness analysis. This is very important for me to train my students. That's why
Yes, ma'am.
if you can have a unclassified copy of your slides, clearance, or I don't know. I mean,
this
just
is all public. This is
all
public
public,
domain.
so we'll put it on the ULI website, we'll update the ULI website and so on. Irene, do you have last minute questions? So I'll look forward to your slides. Let's see if Irene has questions, comments, so she's here.
No, I do not. Thank you. That was very helpful, and slides would be fantastic. Because I'm looking forward to digging into some of the details.
Yes, ma'am. I will forward
Thank
those to the team.
Thank you. Thank you, Chris. So thank you everyone for joining, and sorry for the glitch with connection in the beginning. So we'll start using Teams. It will be smoother for Irene and industry people and all the externals for Illinois. Look forward to the next one. So we'll have Cyan next time, presenting it maybe with Lynn, I don't know, showing Lynn's work, or Lynn can share part of the time if Cyan, I don't know, is not willing to present Lynn's work. So we'll move fast. We'll make sure we get this V&V going, TRL levels and so on. And we'll share the 2-page draft of Lynn's paper with Cyan with you to show how Cyan's tool gets applied to V&V L1, okay? Thank you, Chris.
Sounds great. Thank you, Nara.
Thank you all. So let's close the Teams. Thank you very much. Bye-bye.
Have a great weekend. Thank you.